Good day, and welcome to Africa Teen Geeks. This is the STEM Digital School. Hope that everybody is feeling good and is in the right place. If you have just joined this classroom, this is the grade 12 Physical Sciences class. It's the grade 12 Physical Sciences class. Today is the 21st of July 2020, and we still continue with the Doppler effect. Who would have known that the Doppler effect has so much work and so many problems? I mean, yesterday we did most of the problems, but we could not finish them because there are so many. And it's great that we're doing this because already it's part of the revision for assessment on the 23rd. So on the 23rd, please guys, book a date, make a date, and make sure that you are part of the assessment date. What's good about this assessment is just for you to test your mind. We're going to be going through some exam paper, and after that, you're going to be able to do revision. So on the 23rd, we're not really going to have class. What we're going to have is a test time. So you guys are going to be writing from that 30 minutes that we're going to have. And after that, you're going to put your stuff together. And the next day, which will be the Friday, then we're going to be marking everything. Okay. So I hope that it's easier to understand. But guys, please, it's all about discipline and you trusting yourself to be better in physical sciences. Because if you're going to be cheating yourself, you're going to be cheating yourself, and that's going to be not going to be good for you because you won't be learning as much as you need to. Reminding you that I'm working from the Siavula and the Study and Math textbook. So if you do have them, please make sure you open them, or any other CAPS approved textbook is fine. But since you guys are doing matric, I know you like going into many different textbooks. So you guys can go and download Snaplify, which is an application that has different types of textbooks. So you guys can go and get yourself Snaplify. You can view your textbooks online and offline. They're absolutely free until the 31st of December 2020. So get yourself some Snaplify and get yourself multiple textbooks. I am Nonkulego Madondo, and I am your physical sciences grade 12 teacher. So I hope that everybody is having a good day and ready to do some Doppler effect as we continue. We did from number 1 to number 7 yesterday. So today we continue from number 8. Okay. So it says here, a jet plane is flying with a constant speed and a constant altitude above a school laboratory. Okay. So a learner in the laboratory uses a microphone and an oscilloscope to get the following trace of the whining sound emitted by the jet as the jet flies away from the school. So this could have been easily been you because it's some science students that just felt the need to test the sound emitted by the jet using his oscilloscope and microphone. Okay. So what they want to know here is, please find the wavelength of the sound in meters. Okay, the wavelength of sound in meters emitted by the plane as it flies away from the school. Okay, so they want to know the wavelength when it flies away from the school. Number B, they want the frequency of sound calculated in A. So they basically on A and B, they want the wavelength and they also want the frequency of sound. Okay, so number C, it says, if the actual frequency of sound emitted by the jet engine is 30 kilohertz, determine the speed of the jet. Okay, so basically, we do have our formulas. And remember, if the source is moving away from the listener, then our VL becomes 0, right? And our VS becomes a positive. Okay, just remember those few keywords. So let's go to the answer. So it says here, the wavelength of one complete wave is 2 centimeters, right? And where do we get that from? If you look at this problem here, this a complete wavelength is 1 from here to here, and here it's a 2 centimeter. So basically this one is a given because you just have to be able to understand what is a wavelength, and it's from 0 to where. So if you place it here, this is going to be half a wavelength, but a full wavelength is up until here on the 2. Okay, so the positive and negative waveform. Okay, so we continue. And then now they're looking for the frequency, right? So for this case, we're going to use the formula of velocity is equals to frequency times wavelength. Why are we using this formula, guys? We're using this formula because they said from what you got on A. So these two are related. So basically, once they say they want what is related from A, that means they want you to use the equation that's going to be the relationship between the frequency and the wavelength. And the one way we can get that is if we use the velocity formula, which is equals to frequency times wavelength. Okay. And from there, now we can make the frequency the subject of the formula. Okay. So when we do that, it's going to be 340 meters per second. Velocity was not given to us, right? But we know that the velocity of sound is the speed of sound is 340 meters per second. So that one is a dead given. You should always know it. The velocity of sound is 340 meters per second. So now you can divide it by the 0.2 wavelength, and that's going to give you 70.17 kilohertz. You see the difference here, guys. The velocity, the frequency becomes so high when the wavelength is very small. So which means that the shorter the wavelength, the higher the frequency, right? And the frequency is involved in the pitch, which means you'll hear a louder sound, basically, okay? So that's the difference. The shorter the wavelength, which in this case is 0.02 meters, the higher the pitch of the frequency of the pitch, okay? And if the wavelength becomes longer, that means that our frequency becomes lesser, okay? And which means the sound becomes lesser, okay? So I hope that makes sense to you guys. So the source is moving. They wanted us now to calculate the velocity of the source. So the source is moving and the listener is stationary. We use the equation, like I've already mentioned to you guys, that your VL is going to be 0 because the listener is standing still. Okay, the listener is not moving, so our VL becomes 0. And then the V is going to be positive. And remember we already calculated the V there because they wanted to know what is the velocity of this wavelength when the aeroplane is moving away. So already it's a positive answer because when a source is moving away from the listener, the VS becomes 0, right? The VL becomes 0. So here, now we're going to cross multiply. Remember what we did the last time? We first divide this VF1, we divide the VS, and then you swap them around and you make the subject of the formula, right? As you can see here, there's minus 340 meters per second. So you're going to manipulate them up until your VS is the subject of the formula. And in this case, it's going to be V divided by V divided by frequency times frequency minus all of this will be minus this V over here. Okay, I hope it makes sense to you guys. And then that will give us 260 meters per second. Okay, so you manipulate everything up until you've got your VS as the subject of the formula. This VL is a 0 and your VS is positive because the source is moving away from the listener. Okay. Then let's move. Okay, let's go to question 9. Okay, I'm just looking for our number 9. Ooh, it seems that we do not have our number 9 here, but luckily for us, we do have it on our textbook. So we could just go there. Don't know how I forgot to add it in there. So what I usually do, guys, I always like putting the question in our slide so that you can avoid going up and down. Because sometimes you find that these programs, they jam when it's time for them to actually work. So that's why I usually, okay, there we are. So there's our number 9. Number 9 says, which is this one here. It says two learners, Francois and Sheena, conduct an experiment to determine the speed of sound. Okay, so Sheena stands with a tape recorder while Francois rides on his bicycle, blowing a hooter, which gives off sound, of a frequency of 460 hertz. Okay, blowing a hooter, which gives, so this is a frequency of the source, right? So a number of frequency readings are taken while Francois rides his bike at a steady speed of 10 meters per second and sounding off the hooter. So what does this mean, guys? It means that we have a moving source because the source is on the bicycle, so it's a moving source. So Sheena finds two sets of average frequencies, which is 447 hertz and 474 hertz. So now what they want to ask is which one of the average frequencies corresponds to frequency obtained when Francois was cycling towards Sheena. Okay, a sound of 460. So when she was moving before, it can only mean that our 474 hertz, because it becomes louder, frequency becomes higher as the as as the source moves towards the listener. Okay, so which one of them corresponds to frequency obtained when Francois was cycling towards him? Okay, so what was the learner? What was the speed of sound as calculated by the learner? Okay, so let's go and check it out in our slides. So as you can see here, you see the frequency of 474, since this is larger frequency emitted by the source. So as the source gets closer to the listener, the sound will become much louder. So that's why we chose 474, because it's the highest frequency therein. Okay. So number B says the source is moving and the listener is stationary. So we have VS as 10, VL will be 0, and our VS will also be positive because the source is moving and the list. Okay, it depends. When the source is moving towards the listener, the VS is minus, but once he moves away, then the VS becomes a positive. Okay, so we've got the frequency of the source, which is 460, and the frequency of the listener, which is 474, as we have determined over there. Okay, so now we use this equation. But remember, guys, when we use this equation, we need to make sure that we've got our signs right. For example, here we know our VL is 0, so we only have V left there, right? And over here, the listener is moving towards the source is moving towards the listener. So this becomes a positive. So it's going to be V plus VS. And then we have our V Oh, sorry, guys. When our source is moving towards the listener, it becomes a negative. It becomes positive when the source is moving away from the listener. So this time it's moving towards the listener. So that's why it's a negative. So do you guys see how important it is to have the signs right and the conditions right before you do anything? Otherwise, everything that you're going to be doing is going to be absolutely incorrect. Okay. So now we've got our VL. You see, now we've simplified our formula according to the condition of the scenario. And then now what we have to do, we need to get this velocity as the subject of the formula. So we're slowly going to start rearranging the equation. For example, here we swap these two. So this became V minus Vs, and this was V over Fl times Fs, right? So, but we're still looking all of this minus V, right? But they've managed to, oh, this time we're not looking for the speed of the listener. We're not looking for this one. We're looking for the speed of sound. Because I can see here, I just didn't check the problem correctly. So here we are looking for the speed of sound. Okay, so our V will eventually become Vs is going to become Vs divided by 1 minus Fs over Fl. Okay, and this will give you this kind of formula. So from there, now you can go straight into substitution and you can calculate. It's still the same. So you see what was happening. These kids, they wanted to analyze or calculate what is the speed of sound. So the speed of sound, we know that it's 340 meters per second, but they wanted a way in which they could calculate it and find how much it actually is. So what they did, they got their sound sources and frequencies right. They noted them down and put them in the equation. But if you check here, it's 339. So if you round this off, it will give you 340 meters per second. So whenever you do calculate the speed of sound, it needs to give you something close to 340. Even if it gets asked in the exam, you need to be able to manipulate your answers to get the required answers that you need. Okay. So that's how it works. Then let's move to number 10. Number 10 says to us, okay, what are the speed of sound as calculated? So you see here, like I said, this was what they were trying to prove. We're trying to prove what is a speed of sound. So moving on to number 10, it says ultrasonic waves of frequency 1 times 10 to the power of 6 hertz in a Doppler flow meter are directed at the chest of a fetus and travel with a velocity of 1.5 times 10 to the power of 3 meters per second in the chest. So if the chest moves at a maximum speed of 0.01 meters per second towards the waves and then at the same maximum speed away, what is the change in frequency of the reflected waves? Okay, so this is basically an ultrasound where they use a Doppler flow meter directed at the chest of a fetus. You know, it always happens, for example, for pregnant ladies, when they go for a scan, they usually use Doppler, ultrasonic Doppler flow meters to check the movement of the child. And in this case, they were trying to, they were directing it at the chest of the baby. And now in the chest, so if the chest moves at a maximum speed of 0.1 meter per second of the waves towards the waves, and then at the same maximum speed away, what is the change in frequency of the reflected wave? So we're trying to know the difference in frequencies because you remember what we spoke about, that whenever you're using an ultrasound or a Doppler flow meter, we look for the difference in frequencies between the two tests. Okay. So now we're going back to our answers. So now that it's explained, right, it says there will be two Doppler shifted frequencies, one occurring when the chest moves towards the source and the other when the chest moves away. So the source is the Doppler flow meter because that's the one that's emitting the sound, the waves, okay? So the moving chest is regarded as the source of the sound. Oh, because it's breathing, right? It's breathing in and out. So the moving chest is regarded as the source of the sound, and the receiver of the Doppler flow meter is the stationary listener. Okay, so the receiver in this case will be the doctor, because remember the doctor places the Doppler flow meter on the chest, but the chest is the one that has the sound, and the sound is what is needs to be analyzed, because those are the different frequencies that the sound emits, right? So when the fetus moves towards the flow meter, then there's a specific frequency that it will have. But when maybe the fetus turns around, then it will be moving away from the source, from the sound. But in this case, it will be the baby, right? And the receiver of the Doppler flow meter is the stationary listener. So the stationary listener is the holder of the ultrasound, which is the doctor in this case. Okay, so they are stationary. So the velocity in this case will be a 0. So for the first Doppler shifted frequency, when the chest moves towards the Doppler flow meter, our Vs becomes 0.01 meters per second. Our VL becomes 0 meters per second. The frequency will be 1 times 10 to the power of 6, and our velocity will be 1.5 times 10 to the power of 3. Okay. Okay, so we continue. So you see here, our Vs is going to be a negative. Why is our Vs negative, guys? Our Vs is negative because the source of the sound is moving towards the listener. So remember these conditions. Always remember these conditions. So from there, you're going to substitute, because we've got everything else that is given us in the question. We've got the 1.5, we've got the velocities, we've got the velocity of the source, and we've got our frequency, and this will give us this value. Okay, but you can always take it to the two decimal places. In this case, it's just going to be a 1 times 10 to the power of 6 hertz. So for the second Doppler shifting frequency, this is now when the chest moves away from the stationary listener. Okay, so which means basically it's when the fetus turns around. Oh my word, that's very cute. So the when the fetus moves away from the Doppler flow meter, so which means that it's just turning. So in this case, the sound is now going to become much less. So our Vs in this case is going to be a positive, and our VL is still 0 because the doctor is holding the flow meter but in a stationary position. Okay, so this is what we're going to have, and we're going to start substituting all the stuff accordingly. So we'll substitute our frequencies, and it's the same, very same method as this, but in this case here it's going to be a positive. So the only difference is the positive there. Okay, and this is going to be our answer. Do you see, guys? These calculations are not so difficult. The main point is understanding how they get to be done. How are they solved? How are these problems broken down? Which formula do you use? So these are the most important things that we need to understand. Okay, then moving on, we go to number 11. On number 11, it says the hydrogen alpha line in the solar spectrum has a wavelength of 656.28 nanometers, right? So if this spectral line in the light from a nearby star is 656 0.315. What can we conclude about the motion of the star? Okay, the hydrogen alpha in the solar has a this wavelength is a wavelength. If this spectral line in the light from the nearby star is, what can we conclude? Okay, so let's move to our answers. So it says here, the observed wavelength, which is the one from the nearby star, is larger than the wavelength in the reference star. So the reference star is basically the sun. So which means that this wavelength is redshifted, and hence the nearby star is moving away from the sun. Remember, guys, what redshifted is? Redshifted is when the light moves away, the source, the object moves away from the source. So it's slowly moving away, so it becomes redshifted because the wavelength becomes much larger. Okay, so in this case, it will be redshifted. So that's the answer for number 10. Number 11. So going to number 10 now, we're almost done. It says here, the emission spectra of 4 hypothetical galaxies are given alongside. Okay, so this is A, this is B, this is C, and that is D. So which galaxy or galaxies is moving towards galaxy A? Give an explanation. And which galaxies is moving away from galaxy D? Okay, so galaxy D. This is galaxy A. So which galaxies are moving towards? I think it would be likely number B, right? It's moving, they all moving closer to A. But let's check out the answer. So if galaxy A is chosen as the reference galaxy, we notice that the lines in the emission spectrum of galaxy B are shifted towards the blue end. They are blue shifted towards increasing frequencies, and hence this galaxy is moving towards galaxy A. Okay, like I just mentioned, that B seems to be the one that's moving closer to A. So if this one is number D, galaxy D, this is our reference right now for number 2, is which galaxies are moving away from D. So we check, this is our line right here. So it would likely be C. It would likely be number C, but let's check what our true answer is. Yes, if galaxy D is chosen as a reference galaxy, we notice that the lines in the emission spectrum of galaxy C are shifted towards the red end, i.e., they are red shifted towards decreasing frequencies, and hence this galaxy is moving away from D. Okay, I hope that it still makes sense to you guys, because you know the whole red shift and blue shift thing, it's good for you guys to understand it. You see how what kind of a questions that could be asked with regards to those ones. So make sure that you know them and you understand them. Okay. So now we have to move to our final question. But I see that once again, it's not part of our slide here. So I'll quickly just go in there and extrapolate and take the question from there. Okay. So on number 13, it says that the emission spectrum of helium is observed in the laboratory, and the frequency of bright yellow line is found to be 5.1023 times 10 to the power of 14 hertz. The frequency of the same helium yellow line as observed from the 3 different stars are as followed. So we've got star A, star B, and star C. Okay, so now they want to know an A. Which one of the stars has redshifted in its yellow line? Is this star moving away or towards the Earth? And number B, which one of the stars is closest to Earth? Okay. So this one is our Earth, and these ones are our stars, right? So this is Earth because the laboratory is obviously in our planet in Earth. So now they want to know which one of the stars has redshifted. So a redshifted star would be the one that is the furthest of all the stars, because anything that redshift is what moves away. Okay, so the light spectrum becomes much more less because it's moving away from the source. Okay, so in this case, which one is the one with the highest frequency, with the lowest frequency? So the one with the lowest frequency, remember guys, the lowest frequency means the biggest wavelength, right? So in this case, we must find the star with the lowest frequency. And in this case, it will be the one that says it's star B. So star B has the lowest frequency out of all of them. So this would be the star that has redshifted and is moving away from the Earth. Okay, because redshift means that it's moving away from the source or the reference planet or star, etc. in the galaxy. Okay, so this one will be star B because it is redshifted and it's the one with the highest frequency but longest wavelength. So it's moving away from the Earth. So which one of the star is closest to Earth? That one would be the one with the highest frequency. Okay, so in this case, it would be this one that says 5.1093. Okay, because it's the closest. But I think it's number C, guys, because you check the distance. If this had to be 5.109, it would be a bit after. And it would be like if this is 2, 3, 4, 5, 6, 7, 8, 9. So it would be 0.006 away. But the 5.105, it would be just 0.003 away. So I think star C is the correct answer. That will be the one that's closest to the Earth. Okay, I think this is all that we had to do with regards to this. And guys, please remember we have an assessment on the 23rd. So please allow yourself to understand these problems and be able to solve them on your own. Because if you can solve all these problems like you've been doing them since yesterday, trust me, there is no problem that's going to defeat you when it comes to the Doppler effect. And remember, guys, this isn't a trick. This is a do or die. Okay. Okay. So this is the end of our classroom. So if you have any questions or problems, you can get me on t3tt@gmail.com and I will try and assist you wherever I can, right? And thank you guys so much for a beautiful classroom. Let's meet again tomorrow. We will do some more revision questions. We might do a bit of work, energy, and power just to get you guys ready for the assessment on Thursday, the 23rd of July. Okay. Thank you guys so much and goodbye.